Well, hello. It's 10 o'clock Eastern Standard Time, and welcome to the webinar here where we're trying to figure out all this stuff. Hopefully, you see a screen that says welcome and um, welcome. The idea behind the webinar was to sort of provide a kind of quick tour. If you can hear me on the microphone, just shoot me a note, I guess. I know we're going all over the world, and there's a lot of different time zones and probably a lot of different internet connections. So yes, thank you. Somebody just told me that they can hear me. All good in California. Thank you. Hearing me clearly. Thank you. Uh, I don't want to get too involved in switching the mic over and stuff, but if in the course of the uh, conversation, you have a question about something, I'll try to address that in our comings and goings. So the webinar is in two parts. The first part is kind of a dry run through the software because I thought that if I had a static version of the software, I could do two things. Number one, go through it in kind of a more formalized manner. But number two, I gave a webinar once to the Scientific Affairs Committee that involved having to use parts of Datapunk. And of course, that exact moment, the internet service provider decided to do an upgrade. So I had no internet. So the other thing that this does is this also obviates the risk that later on when we turn it over and go to the web to see how the program performs, that we will still have had this very staticky version of the whole thing. So it's just kind of a double sort of redundancy thing. So away we go. Basically, about 6 months ago, I got sort of intrigued with the idea that there was this tremendous capacity to access this information that was available through services like 23andMe and some of the others, Illumina, Ancestry.com, that involved taking the SNP data that was available from these services. And since the cost now is so affordable, it's really within the reach of most people. And I looked around and I saw that there were a couple of different reporting services. 23andMe originally had a reporting service. And I think the government got in their way, and then they're going back and forth. And will 23andMe have a reporting service? Probably they'll be able to do something, but because of the nature of how they have to present data directly to the public, it'll always be hamstrung by a certain reticence on their part to get too much involved with the gory details of the significance of some of these SNPs. I assume you know what a SNP is. I assume you've understood that there are variations that occur when there's a substitution of one nucleotide somewhere on a gene, and there are at least 700,000 SNPs that are reported by 23andMe. If you go into Google Scholar and look around, you find that the vast majority of them simply have no significance whatsoever, and that doesn't mean they're not important. It just means that we can, with technology, isolate far more SNPs than we can subject to epidemiological data or causational type data that would be able to give us information about their medical significance. So I'll be generous and say that out of the 700,000 SNPs that 23andMe reports, probably about around 3,500 are probably medically significant, and that number will grow as obviously the research environment catches up with the technology capabilities. So basically, I have written software largely my whole life, various forms and various machines. And some of you are familiar with all the Datapunk stuff that I wrote, and some of you use the Swami diet software that I wrote. These are all, hard-coded programs that basically do things, medically significant things, hopefully. And they're written typically in a language called Perl, which underlies the dynamics of the program, and then Perl basically then writes the HTML and all the snazzy stuff that goes up into the web browser and creates the interactive part of the whole thing. So deep down inside, all the calculations are being done by Perl, you know, the data manipulation, the analytics, and all that kind of stuff. And that's where that first concept comes from. Tim Toady, that's a Perl sort of a slug. It just means there's more than one way to do it. And in Perl is a very versatile language, and you can do the same thing 20 different ways in Perl. And it's been a kind of a keynote in how I approached doing Opus, that there's more than one way to look at an outcome. There's more than one way to depict the information. There's more than one way to visualize the information, and people have different strengths and weaknesses with regard to that. I also think the important part is let the technology do the work. If it's at all possible, remove all the drudgery. If there's large amounts of data and it generates large amounts of tables, and I mean, I get cross-eyed when I look at tables, so you know, I think that in many respects, I think we can use the technology to simplify a lot of this, make the information visual. But this is the last one. This one here is really important. Teach. You know, this is a very fast evolving field, and not everybody knows everything there is to know about everything in having to do with genetics and SNPs and epigenetics. So what I wanted to do was to produce an environment that was rich in terms of its teaching possibilities, that you can go into this program and work up a patient and come away going, gee, I learned like new things about this whole thing, things I'm going to want to take someplace else and enrich. And so the idea is that it's more than just, okay, I'm going to plunk the person in and get the data out. It's also designed to be an exploratory tool to make people better informed and make them smarter about the whole field itself. Maximum information, great robust base, ever-growingness. The nature of how you design programs is that the really good programs are always on a bedrock of information, and those information relationships can extend outwards and grow, sort of like the stalk of a cauliflower expands out into the, you know, the flowery part of the cauliflower, or the brainstem extends out into the cerebral cortex. You start with a very good base, and then you just gradually can continue to sort of expand outwards. I think a community basis is kind of nice. Having people share what they know and make it available to other people is helpful. And it should be generative in the sense that the capacity of the technology should lead us towards a better understanding of the interrelationships of anything that has to do with the nature of being able to identify greater than relationships. I got somebody here who's saying that he's not getting any audio. Can somebody shoot me a message that says that they are getting audio? And this way I can just tell that person that it's probably something they have to resolve on their end. Let's see here. We are getting audio. Thank you. Okay, so I'm sorry to inform the person that that may be a problem on their end. So you know, this is a 23andMe printout. You know, and it goes on and on and on. The number on the left is the identifier of the SNP. Then there's an identification of the chromosome, and there's an identification of its position on the genome, and then there's the client's genotype. So in this case, we have a person who has a C and a T at this particular SNP. And that's pretty much what you get. You have to then take that raw data and turn it into something feasible, hopefully human and understandable. In this case, for instance, we could take a few SNPs and be able to calculate an ApoE4 genotype. This here is a demonstration of what's called an algorithm, and that runs inside of one of the apps in the program called LUMEN. In this case, basically, we're looking at two SNPs here on the ApoE4 gene, and the program gets the outcome of the client genotype, and then basically sort of subjects it to a conditional type of analysis. For instance, is this genotype, if it has a C, do this. If it's TT, do that. If this SNP has this and this SNP has that, do this. And so this really is the major power of Opus 23, because, if you look around at some of the other things out there, most of the simple tools essentially report just, SNPs in terms of sort of tabular data, and sometimes some do that better than others. So what we wanted to do was just make the program, visually appealing. The interesting thing about humans is that they're tremendous animals at pattern recognition. Matter of fact, the studies show that second place isn't even close. We recognize patterns to an infinitely greater degree than we just basically handle linear data. And so anytime you can kind of convert something into a visual reference, it becomes that much more intuitive and that much more easy for people to understand in terms of the significance. So the only thing basically that was the major sort of buzzword of the whole thing was to ensure the sanctity of ensure the sanctity of the data. The important part there is that, this is a very evolving field, and you have a significance of certain things that have high value, some are not so high value. And, to simply just put a simple fact together, if this SNP has this, then do that, the machinery will do that just fine. But the problem arises for a couple of things. The single biggest one is what's called strand orientation. Your DNA can be read in two directions, and so when somebody reports a new SNP, they will report it whether or not they went upwards and sort of got what's called the plus orientation, or they got the negative orientation, they went the other direction. And strangely enough, the major database of all this is called dbSNP. That's where you go when you discover a new SNP and try to get it accepted as an official recognized SNP that gets an RS number or things like that. But the problem is that they'll take data either way. They'll take data that's on the plus strand orientation or data that's on the negative, which is kind of crazy because, amongst other things, 23andMe reports all their data on the positive strand. And so now you have to get that thing taken care of. And that's important because in addition to everything else, a lot of times the researchers, when they report an outcome, this particular SNP has been associated with atopic dermatitis. We found that the risk allele was C. And then you realize that they're reporting their results on the negative strand. So now you have to reparse that back to the positive strand. And this can sometimes cause confusion with consumers as well as physicians. This is a printout from NutraHacker. And you'll see here that the expected allele here for this cytochrome was A, but the genotype risk, as they explained to the client, was C and T. So the question arises as to how the poor client is going to understand that this was on one strand and this is on the other, and they probably converted the A to T when they folded the strand back, but they didn't do it in the column here such that the consumer would know what the heck they're talking about. So, and this is kind of an issue that you see a lot, which is, what's the strand and how come some people say C and some other places say G. And the problem with a lot of this tabular data is typically when they report the results, they'll send you to dbSNP, which looks like this. Now, I think this is wonderful stuff, and you can get a lot of interesting material out of this, but it's just not user-friendly, and it doesn't really have a whole lot of significant clinical data. This is really the sort of basis of where the SNP resides. And you have other places like Snipedia, which is a kind of a more user-friendly site that gives information as well. So sometimes the tabular data, they'll send the person to Snipedia, and they'll have to fend for themselves. Beyond that, what to make a sense of this. And of course, Snipedia has issues with strand orientation too, because they might report a clinical study and it shows one particular nucleotide, and then you look up on the top there and it says, DB orientation is negative, but they give you a result that says positive. So one of the things that really, the first thing I did when I wrote the program was write the editor, because it doesn't pay to have a wonderful program that doesn't have a tremendous capacity to be able to be confident that the data has very high veracity. So when you add a SNP to Opus 23, you go to an editor backend and a dashboard that sends out a variety of different robots to all these different sources and parses all that information and brings it here, so that at the moment that the editor is sitting at this editor desk, they've got a tremendous amount of information. As when we go live, and if all goes well, I can show you this. But that moment, they're sitting on top of probably the most intense aggregated information on that, so they can make the most accurate assessment. And again, I think that that's just where my head is as a data scientist, which is it doesn't really pay what you do, and it doesn't really pay how nice you do it. If you can't trust the data, well, it doesn't really matter, does it? So basically, here's an idea of where all the data comes from into Opus 23. It comes from dbSNP, it comes from SNPedia, it comes from HapMap. GWAS are the genome-wide association studies, which we'll get to in a little while. PPI are the protein-protein interaction databases. PharmaGKB is the pharmaceuticals, more of a pharmaceutical leaning with regard to nucleotide and SNP data. Online Mendelian inheritance in man, PubMed, Idiome, Diseaseosome. I actually didn't even put them all in here. But the reality is that the wonderful thing about writing computer code at this time and place in the universe is that most of this stuff is open source. In other words, you pay your taxes, and NCBI produces all this wonderful data, and they make it very easily for people like me, programmers, to go and grab that data through what are known as APIs. The API is like a hand-holding thing. So if I need something on something, I can ping GWAS and get the data on that, PPI. A lot of these databases are, freely available. Some of them are humongous. And that's really one of the advantages of why I continue to work with Perl, because Perl, when it comes to text manipulation, is blisteringly fast. It was used, actually, it was the thing they say that saved the Genome Project, because they couldn't, back then they could only do small sequences, and they had to look for periods where it overlapped to be able to put it all together. And that capacity to find sections where you could find where the end of one and the beginning of another had a certain number of sequences was computationally very, very difficult. But Perl was able to rescue that because it has just tremendous capacity to work with text. And so even though my daughter uses Python and has convinced me that Perl is sort of like the flower-painted Volkswagen of computer languages, if you go into bioinformatics, it's still the language of bioinformatics because it just processes text just so fast. One of the things that we try to do in situations where you have lots of different capacities is I love what are called mashups, where you take data from one place and data from another, and you kind of make something snazzy out of it. And one of the things we did here was to take the PubMed references that control gene expression and have them relate to the interrelationship of natural products. And so we have an entirely unique curated database of articles that are curated, that are identifying expression data on genes that are under the control of natural products. And you'll see later on this leads to some interesting capacities as far as therapeutics and prescriptives. But let's talk a little bit about the program. The first area I'd like to discuss is mappings. Mappings are just generally, they're known as pathway maps, signaling maps. I love maps. I love images, as you know. If you've used Quadlibet, I love maps, pathways, and things like. I love networks, So I thought, gee, I like networks, and I like people, and I like genotypes. Why can't we make a network out of the person's genotype? And so, for instance, there are a lot of pathway maps in Opus 23 that you can click on. For instance, this is, if you go to the pull down and get detoxification networks, you can see here we got cytochromes and glutathiones and oxidative stress gene expression. And then you see how the maps are colored. Well, they're colored with the person's genome. And so, in essence, if the map is got a green color, it means that person has no at-risk SNPs in that area. If it's green with yellow, it means they have some no-risk SNPs, and they're heterozygous for some risk SNPs. And if they're orange, they're completely heterozygous for the risk SNPs associated with that gene. And each of these maps is clickable, and it brings up an information pop-up, as you'll see. Here's a map in detail looks at estrogen metabolism in the liver. So you can see here, I would make a quick case that there's probably issues in cytochrome, 1A is involved in oxidation and hydroxylation reactions. And so this is a person probably who is likely to have some toxic intermediaries that may be stressing out their phase 2 stuff. In addition to showing the genotype in the map, you can click up here where it says power analysis, and it converts the map into sort of the battery indicator on your iPhone. You know how like when you start losing power, the battery starts kind of getting smaller and smaller? Well, this essentially kind of tells us just what degree of functionality can be expected from that gene given the outcome of those SNPs. So it's kind of like the battery report on this. And you'll see later on, these things are clickable and they bring up a wealth of information. So the second part of the program is the informatics. And these are mostly different apps. I think there's about 9 apps in Opus. The first series of apps are queries. And probably the most useful one is ARGONAUT. ARGONAUT allows you, it's a filterable search/table. So for instance, if I was to go in here and put in COMT, it would bring in everything that had COMT in its descriptive. And then you could click on here and it would bring up a pop-up for the gene. You click on here, it would bring up a pop-up for the SNP. If I was to click on cancer, it would bring up every SNP associated with cancer. And here it shows us the risk allele is T. This client has CC, so the outcome is nice. This is not a particularly high magnitude SNP. Some of these are more high magnitude than the others. So the idea here is that you're getting, again, this idea of presenting data in different ways. There's a couple of other ones that are a little more esoteric. Wanderer is kind of a smart search engine for the whole site. So you could put in something like COMT and it would bring up all the algorithms that are available for it, all the other scenarios. In other words, it goes through the site and finds all the places that COMT gets examined. And Rarify is kind of a unique, it's kind of an app that you don't run a whole lot, but you should run it, because what Rarify does is it looks for SNPs that have a distribution of 1% or less. So in other words, these are SNPs that the particular risk allele is found in less than 1% of the population. And so consequently, it's probably likely that in the case of the person having a heterozygous mutation for that risk, it's going to be probably pretty significant, because it is most of the time going to be the rare SNPs that are going to be the ones that are going to be more clinically significant. Here, we run it on this patient, and they were heterozygous. Most of the time with rare SNPs, is heterozygous actionable? Maybe yes, maybe no. SNPs vary in terms of degree of functionality that's associated with a heterozygous condition. In some SNPs, the function of the gene might perhaps drop minimally. Other times with a heterozygous for the risk allele, the function of the gene can drop as much as 30–35%. So that's the sort of area of the website where you run, hey, I want to find out about something really fast and get some quick and simple answers on things. And you have to remember, at any given moment, you've got a patient loaded in here. So as you're running these apps, they're running on the patient that you've loaded. Then you can go load another person and run the same thing, except it's on a different person. Then you get into the apps that are basically called analytics. And these fall into 2 categories. There's one app called MOBOCASTER, and I'll bring this up later in the real world. MOBOCASTER basically looks at syndromes in terms of what are the most common genes associated with those syndromes. So in other words, it looks at a syndrome like HPA axis, and then looks at the most common genes that are associated with the HPA axis, and then brings up the SNPs that are associated with those genes. But it also does a lot more, as you'll see when we fire up the live version, because it actually gives you etiological data and lots of other things that might be important with regard to looking at the patient as a person who has maybe perhaps elements of these etiological factors that may actually play more into the significance than some other person who didn't. And that's the power of using this idiome, which is like the genome of etiology out there. And SUPERMOGADON is this. So this is the second analytical app. This is what's called a Manhattan plot. A Manhattan plot is named after the fact that you're supposed to think of this as sort of the Manhattan skyline. And what you have here is all the chromosomes, and then you have, for type 2 diabetes, all the SNPs that are listed for those chromosomes that are associated by the genome-wide association studies. So these are all the SNPs that have been reported to be associated in some way with type 2 diabetes. And what makes it really neat and gives the Manhattan in Manhattan is that the SNPs are oriented as a negative log of the p-value. So in other words, although we tend to like to think of p-values desirable in terms of their smallness, in this case we reverse it around and we make the p-values reflect importance in terms of their bigness. So in this case we have a SNP here, which would be something very significant, as would be this, this, and this. And then the way you interpret this is that this is a SNP that the person has homozygous for the risk allele, homozygous for the risk allele, no risk allele, heterozygous for the risk allele. So when they're square, it means we have them in the Opus 23 database. And when they are in circles, the gray circle means that it's not reported by 23andMe. The blue circle means that we think that it is heterozygous, homozygous for the non-risk allele. And then certain instances we can actually get that information as well. So this would be a SNP that we don't have in Opus, but is in 23andMe, and we do have some data that indicates that it would be a potential heterozygous for the risk allele, and it would be on chromosome. Now, if we were in the live version, I can show you that when you mouse over these things, it actually tells you the gene, and you can zoom in and all sorts of other cool stuff. And then, of course, you can go up here and put in another disease. Matter of fact, you can go up here and put in acne and AIDS, and it will give you the the sum total of what are the SNPs associated with this combination of pathology and this combination of pathology. So this is really quite powerful function because A, it's visual, B, it takes a lot of very dense, difficult data and subjects it to very visually appealing simplicity, and it goes right to the heart of the matter of what it is that should be a significance with regard to that patient. For instance, here we have a very significant situation here with this particular gene, which this is a slideshow, so I can't mouse over it, but later on perhaps I will. And we got algorithms. And I sort of showed you those in the beginning when I talked about the APOE4 algorithm. Algorithms basically, I think it's an Arabic word. It's just solving something in a sequential process. So if I had an algorithm for getting up in the morning, I might start by eyes open, check clock. Is it time to get up? Yes, get up. No, stay in bed. It's really that simple. And probably the major element with algorithms that are their power is that they can be extremely convoluted, much more to the point that you and I would ever be able to figure them out, but computers can figure these things out very, very easily. And in the case of Opus 23 rather, what algorithms do is they give us the opportunity to look at complex multi-SNP relationship and outcomes that typically find their way into things called haplotypes, which are, if you get one of these, you get two of those, and if this is found with this. And a lot of times these haplotypes may or may not exist on the same, they may not even exist on the same chromosome, let alone on the same gene. And sometimes that has to do with what's called epistatic relationships, where the protein produced by one gene controls the expression of another. And that's called PPIs, protein-protein interactions. And the fundamental aspect of an algorithm is in Opus 23 is that at the end of it, it just tells us yes or no. Okay, so we write the algorithm and we ask it, if this SNP is that and that SNP is this and this is that, then true. And if not, then this. But and there's like 230 algorithms that are in here, and they're easy to write. And there's a lot of literature on these things where they do talk about, as I said before, a lot of the common illnesses that have genetic factors. Like I said before, things like atopic dermatitis or migraine headache. That this is the only way you can make sense out of at least their genetic basis with regard to variations and polymorphisms. And this is an algorithm, and I'm sure you probably don't need to see. And all I really want to direct you to is just the nature of it. The genotype of the client is this big variable, right? And so if we ask this thing to get us the result from this, and if it happens to be AA, we do this. If it happens to be AG, we do this. If it happens to be GG, we do this. And then we print out whatever needs to be printed out. So in this case, this one was done by Dan. It's associated with endometriosis, endometrial cancer, and age-related cognitive impairment. So, an algorithm is really just kind of a little program that floats around inside the other program. And like I said, if you've got the data, they're easy to write. And I can later on we'll see when we talk about an app called Cluster. If you got one you want to just take out for a test ride, you can do it yourself, just using almost like a smart playlist function. Here's where the power of algorithms really plays out. I mean, this is, again, I hate to make a case for NutraHacker, but this is a justification of being able to make a call that the person is a NAT2 acetylator, essentially. So in essence, basically, what you're looking at here is the determination of a person's acetylator function, right? And in this case, they looked at these two SNPs, and they were able to at least feel comfortable enough to say this. And that's not uncommon. For instance, if you look at a lot of the reporting software, they'll look at a particular cytochrome or two, and they report it as sort of very, very definitively able to make that statement. And on the right rather, you see a tiny portion of the algorithm that's used in Opus 23 to calculate N-acetyl transferase 2 intermediate metabolizer. This algorithm, in order to do this, is 4,000 lines long. Okay? The reason being, as you can see, it uses 6 SNPs. And each of those SNPs is capable of 4 possible outcomes. So you have 6 SNPs to the power of 4 possible combinations that might possibly indicate that the person is an intermediate metabolizer. So, the question arises is, which one do you think is going to be a more accurate assessment of this NAT2 status? Just one single isolated SNP? And again, this is typically the case with regard to cytochromes too. They'll look at a particular cytochrome and they'll say, well, this is the case that might indicate that there's some problems with this particular cytochrome function. But for instance, when you start looking at things like CYP2C19 fast metabolizer, you actually literally have to count about 10 different SNPs, and then you set a sort of a threshold. If 7 of these 10 are this way, then the person is a CYP2C19 fast metabolizer. So, I think one of the nice things that Opus does is it kind of, in a way, kind of really does embrace the fact that this is not as simple as we would like it to be, but it needn't be daunting, especially if we let the technology do the work. The interesting thing about algorithms and the way it's designed in Opus is algorithms can call other algorithms. So for instance, in this case, an algorithm that checks for early menopause can call another algorithm to see if the client is female before it runs the rest of the algorithm. An algorithm that checks for B12 metabolism via Cuban can call another algorithm to check for secretor status and factor that into its determination. If the person's a non-secretor, their level of B12 assimilation is going to be a little bit higher. And again, I've changed this. We're at about 235 algorithms. And it all goes back to letting the technology do the heavy lifting. Basically, this is the LUMEN screen. As you're seeing here, a depiction of the various categories of algorithms. So for instance, we have 13 algorithms under polymorphism. We have 24 algorithms under neurodegenerative disease. We have 21 algorithms under autoimmune. And it's telling you here, some algorithms, the person had some beneficial effects with the neurodegenerative. A considerable number of them were problematic, but the vast majority of them, they didn't ring true for that person. In this case, the mind-body, it's significantly more serious problems there, perhaps. And you can click on, when you're in live, you can click on this and it brings up all the algorithms. And if you click on this, it just brings up the bad ones. And if you click on this, it brings up the good ones. Here's an algorithm. I've been sharing a lot of these on the Facebook page, and this one's pretty. I just wanted to find one that was happy news, rather than sit there and show a, terrible thing. In this case, this particular client had issues with C-reactive protein that would indicate from the outcome that they're probably, if they were to go on a weight loss routine, they probably would not experience C-reactive protein mediated inflammation with weight loss. If they increase their intake of dietary cholesterol, they probably would not see an increase in their CRP because of this outcome down here. Okay, and you can see as the algorithm takes that very complicated thing in there. Look at the interpretation. Very simple, very easy to understand. Always has the PMID. If there's a statement about something that's being definitively made, it always comes with a PubMed identification number, and that's a clickable link as well. So it says here, this algorithm uses a combination of major minor L's to determine possible nutrition-related relationships. I was taking a look at this algorithm before I copied and pasted it to the screen, and it turns out that depending upon these three outcomes here, there's a total of 21 different things that can show here depending upon this. Obviously, you could probably wind up with a situation where there would be some bad things showing up here as well. This is the Apple iTunes Smart Playlist. So if you were to go to iTunes and make a playlist for yourself, you might say, hey, I want to make a playlist of all the David Bowie songs, but I don't want any of the songs where David Bowie's with Iggy Pop. Okay? So here's a simple device that allows us to make a smart playlist that is essentially going to give us, it'll go and make a playlist without us having to go and dig up all that stuff. And it'll find if Iggy Pop's on the song, it's not going to put it on the playlist. This is called a Boolean function. Boolean is just fancy for sort of the world of 0 and 1, true, false, yes, no. Boolean's black and white, all right? So and what you can do is you can see here, match all of the following rules, right? So if I change this to any of the following rules, this would change. I would get all the songs that had David Bowie and any of the songs that didn't have Iggy Pop, which probably wouldn't give me the playlist I wanted. So this idea of all or any is actually, again, very powerful because just by changing all to any, it changes the entire makeup of the playlist. And there's an app called Cluster that does just this. Let's say I decide I want to check a couple of snips and run it on my client. I can make a playlist and fire it up, and out comes the result. The cluster was false in this case. This is where the community part kicks in because I can save, if I have a particularly neat cluster, I decided, wow, I really want to look at the estrogen receptor with regard to such and such, and this is my great little cluster here, I use it all the time. Well, you can save it. You can save it into your toolbox, and you can publish it to the community so that other people would be able to use it as well. So it would become, my famous new estrogen receptor migraine headache cluster. And maybe if it got really well liked, it would be, something that would be open to being incorporated into the regular algorithms. So cluster is kind of cool because, again, it just allows you to very simply ask some simple questions and get some answers. If RS1234 has an A, and, the algorithm for rapid metabolizer is positive, then, it would tell you, if the person had that, it would tell you it was true. And you can see over here, here's a client cluster that's associated with this client that shows that Tom Greenfield did a little test cluster that was a simple little thing. If I clicked on this, it would load the client data and put it up on the screen. This is an increase in response to atrial fibrillation and reduced response to therapy. Now the next section is the prescriptives. Did I spell that right? Because there's a line underneath, but I don't know. The prescriptives, basically, there's kind of two things that are going on. Psychic is another app. And what Psychic does is let's say you give it a gene. Okay, in this case, we give it VEGF-A. What Psychic does is it crawls up the PPI network, the protein-protein interaction network, and it finds all the genes that are 3 orders of magnitude upstream from VEGF, and then it goes down the PPI network and finds genes that are 3 orders of magnitude downstream of VEGF. Then it cross-references those genes with the database of our natural products, and it gives you a point where you can control VEGF either upstream or downstream. And you can do weird things with this. For instance, as you see here, we are doing what's called a stimulate block bottleneck. No, actually, I take that back. This is stimulate blockade, but this is actually not right. So what we are doing here is actually this word should say bottleneck up here. I got to change that. But anyway, what we're doing here, when we say stimulate upstream, we're finding all the natural products that have an agonist effect upstream of the genes that are upstream of VEGF-A. And then we're finding all the genes that are downstream of VEGF that have an antagonist effect. And then they're being put together in terms of their evidence significance. So here, if we wanted to stimulate VEGF-A upstream, it looks like astragalus is pretty good. And if we wanted to blockade it downstream, we might want to use maybe andrographis and maybe scutularia. And you can run this in terms of making a various matrix of stimulate, bottleneck, inhibit, drain. So you could, for instance, inhibit this, okay, and drain this, and that would find all the antagonists here and all the antagonists there. So the idea being is that you can kind of almost freeze the thing in place. This is something I'm working on now called FANTASMATRON. FANTASMATRON basically is a nutrient generator. So for instance, you could run this on the client and FANTASMATRON would come back and say, based upon the SNP analysis, it would be a good idea to increase the amount of total folate in the diet, increase the amount of vitamin D, decrease sodium, decrease phosphorus. And then, you hit the button and basically it gives you the foods that are going to be most inclined to want to do that. So, and then you can filter it by using the blood type values or Paleolithic values, Mediterranean diet values, or vegan diet values. So between Psychic and FANTASMATRON, you've got tremendous power in terms of being able to orchestrate your use of natural products with a great degree of intelligence and a great degree of discrete employment. You're being able to go in there and pop away. And the nice thing about it is that even though these programs are really in their infant stage, they lend themselves to the development of more of an AI-based approach over time. So that with time, we start writing the AI scripts that start actually going back and forth and putting the relationships in and things like that. When you first log in, you get to your dashboard, and basically it just tells you where everything is. It gives you actually an interesting feed here, which gives you a feed of all the PubMed links that the editors have felt were important enough to have an impact factor that is worth you maybe investigating in terms of reading. So it's an RS feed of all the high quality articles that we're reading as we develop our SNPs and as we develop our naturopathic agents and so on and so forth. Then you get some information. For instance, when there's a new algorithm that's added, it shows up here. When there's a new cluster that somebody's added, it shows up here. And you can click on these things, and whatever your active patient is, it will run them. So for instance, if you've got an active patient and you go, oh, gee, Peter D'Adamo did something on increased Prevacid concentrations, I'll click on that. You'll get a pop-up, and it runs it on your client that's right there. So anyway, the current status program is wonderfully robust and infinitely scalable. So in other words, I could probably be writing code for this thing forever. And just as things get better and stronger, data structure is solid, new functions easily integrated. We have some very nice, wonderful people who help out with entry of data and curation. It's a wonderful opportunity here to do something. This is generative medicine, basically. If anybody ever wants to know what generative medicine is, this is generative medicine. You're using very complex models, and you're using technology to produce the simplification. And I can go into heuristics and all sorts of other things that are part of it. But the end result is this. We are human beings, and we are limited, okay? But our information is growing exponentially. Now, how do you take information that's growing exponentially and make sense out of it? Okay, well, you could ignore it. You can simplify it to the point where maybe it's just a cartoon version of itself. Or you can find the techniques and the technology to basically use that information and draw some qualitative determination from it and quantitative determination from it, right? And then use it under simple sort of assumptions. And that's generative medicine. For me, I got to finish the help docs. I got to finish that diet generator, and then I got to finish the report generator. These are very, very easy things to do. The hardest part of this program, believe it or not, is making all the graphics and stuff. That's very difficult. And then really designing the data structures in such a way that that going forward it's going to still work. It's going to still be relevant. It's sort of like, talk about a developmental difficulty. If the stalk of your cauliflower's got a problem, well, the flower of the cauliflower is going to have a problem too. And sometimes you can't go fix the flower because you can't fix the stalk. And, data is like that too. If you don't have the right structure from the start, or you don't have a structure that's amenable to alteration and evolution, you don't really get that. You can't expand. But the data structure in Opus 21 is so flexible that really, and as so many of the parts can interconnect and talk, that they can be put together in an infinite amount of combinations. Cost. Well, let me put it to you like this. If you remember the INGM, you would have a license for 10 clients. That license would be about $500 USDA. So it comes out to about $50 a client. If you use NutraHack or some of these others, they're probably not that dissimilar, strangely enough. So I didn't want to go into any big, like super duper expensive thing. I want docs to use this, and I want people to benefit from it. Some of the money that is part of the professional program goes back into the INGM. And if you are a naturopathic physician and you're AAMP eligible or CNPA eligible, you should join the INGM. Go to natgenmed.org. And it's, I think, $100. You get wonderful benefits. And then basically when you put in your IGM data, the cost of the license goes down considerably. If you're not INGM, then you could basically use this. We do vet licenses. So for instance, if we're not going to let people use this program I can't parse their license information and make sure that they are not going to use this for crazy things. And we will, obviously, if I know who you are, I'm not going to call up the licensing board. But if I don't, I may very well do that. And if you can be an INGM member of an associate member, even if you're not a naturopathic physician, and we'll take it on a case-by-case basis. If I know who you are and I know the kind of work you do and you're an INGM associate member, then we'll let you use the program. The neat thing about the program is that once you've loaded a client, you can run it ad infinitum. So if you want to set it up, we can email you and say, hey, guess what? We got a new app that runs, 25 different flavors of ice cream cones on depending upon, some SNP. And then all you do is go back into the program, re-index the client, which is just a one-click thing, so that the new information is incorporated into their file, and then look at the new stuff. So, who knows where this is going? The interesting thing about it is where it's gone so far. I started writing this program in the middle to end of May. And so where are we, in August? I was actually in a meeting with a rather large Silicon Valley marketing firm, And we were thinking of hiring them to do some marketing, but they didn't really have that much exposure to the naturopathic community, and I mean, naturopathic community is very difficult to market to because they pretty much distrust everything, and so they were running things, and I'm thinking to myself, well, this is never going to work with the people I know. But the interesting thing was that they had done a lot of work with Cisco and like big tech companies, and the guy, I asked the guy, well, how long do you think I was working on this program? And he said, 3 to 5 years. And I said, no, I've been working on it since the middle of May. So that doesn't, I'm not saying that to be like super cool and impressive. I'm just telling you how much in love I am with this. I mean, I get up in the morning and it's the thing I just want to do. I just think I can do something new here. Wow, I can do some new thing to look at something different, So, and I don't know. I think it's good for your brains too as you get older. So anyway, availability, we're going to be running it to COE in September, and somebody says I skipped slide 36, but actually I didn't. I kind of went to 37 and then went back to 36 because I had them in order. Thank you. It's going to be at the COE in September, and we're going to run it on patients. We have decided that we are going to do it like this. The patients do the 23andMe independently. They can either get the raw data from 23andMe and bring it in, or they can come in and we'll download it for them. The algorithm for parsing the 23andMe raw data is beautiful. It downloads that whole file, parses it in like 2.5 seconds. It's really something to behold in terms of just how fast it is. And then we schedule what's called a nutrigenomic consult at the COE, and we book an hour and a half for that, and 1/2 hour is spent before the patient gets there running all the things and doing all the analytics, and then we're with the patient for an hour, and I think we're billing about $300 to $360 for that. So listen, I've seen prices all over the place for some really bad stuff that run in the thousands that people are doing, but I it's just not the way, that's not the way I want to do things. I don't produce this stuff with that in mind. So to give you a scalability idea, if you're thinking of putting it in your practice and you want to have something that really is very affordable, because by that time the person's got a huge amount of data on a huge amount of things, and they haven't had a go into hoc to do it. So if all goes well, I'm going to close this window and then I'm going to fire up the browser. So bear with me for a second. What's the key? All right. Can somebody tell me if you see this? You should see like a browser screen. Thank you. All right. Now here's where the big things occur because I never type in my password right. All right. So if this fails, it's just because I don't type very good. Oh, okay. Welcome back, Peter Diadamo. Do you want to load a client? So we're not live. This is what it looks like. Sure, I'll load a client. Should I load Mona Lisa or Leolangio Misterioso? Well, let's load Mona Lisa. All right, so you'll notice now up on here I got a whole bunch of cool things. Well, first of all, let's start off and see. I'll go to detoxification networks. All right, so go to glutathione. Now, I wonder what this is. Oh my goodness, it's a pop-up. So anyway, what I just did is I actually clicked on the link for glutathione reductase. And then, of course, it gives, like I said before, the major goal here is not only just to do, but to also learn. So what we have here is glutathione reductase. We don't have any HapMap frequency data, so ultimately if there was HapMap data, this would be really, really pretty. But it's not there right now. And we do know that there are a couple of things that are agonists and antagonists, and we know that, for instance, we have a glutathione as an agonist in humans, and let's take a look at that. Okay, it's got an impact factor of 4, And this article has these things associated with it. Oh, let's go back. Okay, let's take a look at the SNP. All right. We have a couple of things here with that SNP. Let's go over here and find another one. Well, let's look at this. Cysteionine beta synthase. Oh, there we go. So this shows us that the person's got really a combination of some heterozygous SNPs, and then this is called a drill down. This is the SNP and its outcome, and they have this section. So their genotype is, for this, is 44% of the population. And then again, we see naturopathic agents associated with it, right? In this case, a multivitamin is B9, that kind of stuff. And you can click on these and get that information as well. Let me go back. We could look at how about inflammatory networks. We could look at oxidative stress, right? Look at this guy. Oh, this guy's got a lot of stuff. Curcumin, well, blueberries. And again, here we got an issue here with this particular SNP. And so, and of course, you know, the maps are all, you know, sometimes you get older, you need to be able to see them a little bigger and stuff, you know. So, and again, as I said before, we can do the power analysis on this and get to see what the battery storage is on these genes. And that's the end of mappings. In Manage, you have things like, you know, your profile and tools and how you would load accounts and things like that. Informatics, let's say we go queries, let's go look at ARGONAUT. Okay, well now you see something that looks pretty much like a table, right? But it's a table of like 2,000 things that doesn't want to be a table, it wants to be something else. So I put in COMT and I find, okay, these are the SNPs that we're currently monitoring on COMT, right? We can look at this and get in some kind of, oh, COMT is a big gene. What do we have here? Well, we have that this gene is involved in an algorithm that looks at the heightened placebo effect. It's involved in an algorithm that looks at possible high pain sensitivity, low pain sensitivity, and normal pain sensitivity. And we've got some things that are associated with its expression. Here we go. We can probably pull up something on, whoa, there we have, this is RS4633 is like the big kahuna of COMT. And we, as I said before, the idea here is not just simply to present, but to give you as rich an environment, give me as rich an environment, so that when I'm working this, I'm actually learning. You know, oh my goodness, this is an opportunity for me to become very much more versed in things. This is the HapMap data. These are Europeans, and this is a Japanese population in California, Mexican population. So you just gets to see the distribution of the SNP genotypes across various populations. And in this case, our Mona Lisa is heterozygous for this mutation. So you can also, like I say, if you want to put in autism, you get all the SNPs associated with autism. And then we have the power factors here. So, you know, things like Wanderer is kind of a smart, let's put in COMT here. Okay, so what Wanderer does is it basically gives you a kind of a smart thing. Where does this darn thing show up in here? And you can see this. It shows up in a variety of algorithms. It shows up with a variety of genes associated with it. And again, I'm not, I don't want to belabor the point. You know, the things pretty much work for themselves. So then we got SUPERMOGADON. SUPERMOGADON is our genome-wide association stuff. So for instance, I always told you if I put my mouse over this, I normally should see something. Well, I do, right? Then we have a gene called TCF7L2, which quite frankly, I've made a point that I should definitely investigate, but I still know absolutely nothing about this gene and the SNP. So, I mean, what do I know about this? Not a whole lot. What does this know? This gene encodes a high mobility, blah, 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 so-and-so. Ah, Genetic variants of this gene are associated with an increase of type 2 diabetes. Probably I should know something more. Oh, by the way, there's apparently that the gene is antagonized if you eat a low postprandial insulin diet of rye pasta. Anyway, so if now let's select a disease. How about I don't know, AIDS progression. Not too many. Got one gene here that she's got a problem with. I mean, there's a lot of things you can go in here, like here, bone mineral density, breast size, bronchopulmonary dyspnea, C-reactive protein levels. This is the genome-wide association part of the whole thing. Your tax dollars at work. I can do cool things. If, for instance, if the map gets really weird, I can kind of zoom in. I can kind of even zoom in if I want more. Sometimes, the things will get kind of clustery, and so it's nice to be able to kind of get that under control. MOBOCASTER. This is the one that looks at genes in terms of their relationship to syndromes. So in this case, let's go look at HPA axis genomics. What we have here is the breakdown on a gene basis of all the genes that are associated with a disruption of the HPA axis and ones that really do need to be looked at with regard to this person. So here we have a particular mutation here and a mutation here that probably would be reflective of this. And over here you can see some interesting things, because right here we see that alcohol withdrawal delirium is associated with SLC6A4, and these are the etiological factors that might be part of that. So the program can really do a good job of even presenting you with possible etiological factors that might play in with the further development of a particular syndrome, if the result of the SNPs associated with the genes that are associated with the syndrome are indicative of being of any interest. And then here we would have natural products, and even better, we have here the epistatics. So for instance, here, this allows you to go up and take a look down. For instance, we've got a gene downstream of this and a gene downstream of this and upstream of this. So again, the idea of MOBOCASTER is to look at not necessarily the same things that the genome-wide association studies do, which are largely recognized pathologies, and also to really only limited to the specific SNP indications. Here we're clustering the pathologies underneath the gene and then looking at the genes as they relate to the SNPs. And that's typically, when you read a review article on the genomics of something, that's typically the way the information is organized. It's typically organized by, genes associated with. And like most things, this kind of stuff, we're kind of rolling our own as we go. That, if I wasn't spending so much time writing the program, I could spend more time putting this stuff in. But the fact is, we have a significant amount of this stuff in here already, and there'll be eventually a time when I, don't need to be coding as aggressively, and then I can go back and sort of continue to be using whatever powers I have to make the data better. And what else? LUMEN. LUMEN is the algorithm program. So here we look at neurodegenerative diseases. So I can look here. If I click here, I get all the neurodegenerative links. If I click here, I get the bad ones. So there's 6 bad ones out of 24. So we'll click on that. And what do we got? We got that this client is an ApoE3, ApoE4. There's probably some additional risk of Alzheimer's, not as bad as the other combinations. Person has a 2 long-form serotonin transporter polymorphism. This is interesting because that showed up as well in the HPA thing in MOBOCASTER. There's a few SNPs that seem to indicate some risk factors for autism. It's kind of hard to find a SNP that doesn't give you autism. And here, again, we've got several here. And they can be clustered into, again, an analytical framework. But some are going to be more common than the others, and some are going to be more significant. So oftentimes a good way of looking at this is the power factor. If the SNP if that algorithm's got a high power factor, it means you've got significant situations. Like here, you've got a 1.41 greater risk of certain disorders. Can you explain the power mapping significance in a bit more detail when you get a moment, please? Sure. I'll tell you what, let me just finish this up and then I'll go ahead and do that. So then we get to cluster. And cluster is where I said before, it's like the smart playlist of genetics. If right now, you see, I'm looking at Mona Lisa, right? That's my active client. So no matter where I go, until I tell the program I don't want Mona Lisa anymore, I want El Angel Misterioso, everywhere I go, I take Mona Lisa with me. So anything I do is always with Mona Lisa until I tell it I don't want Mona Lisa anymore. So now what I can do here is, you can see here, I've got a few things. I got a cluster associated with this client. And I've got some clusters that I made in my toolbox, or ones that I like so much I put in my toolbox. And then I have a couple of others that are in the community. So let's run this cluster here. Polymorphism in dietary carbohydrate modulates metabolism of toxins. See what happened? When I clicked on it, it loaded the client, and then it loaded the conditions, and then it evaluated them, and that particular cluster evaluated false. So this cluster does not have Iggy Pop in it, basically, is what it turns out. It's got David Bowie, but not Iggy Pop. Or maybe it doesn't have David Bowie or Iggy Pop, now that I think about it. But you can roll your own. For instance, let's say I want to have a cluster that specifies that you run the algorithm that the person is genotype AA. A blood group genotype AA is positive, is positive. And I want to do an RS blah, blah, blah. This particular SNP should contain A. Then I run the cluster, and cluster evaluates false, even though one of the things was true. I didn't even know to predict that, but apparently this person has, this SNP has an A, and their genotype is AG, so that was true. But they're not blood type A, and they're certainly not blood type AA. And what did I do? In order for this to be true, I required that them all be true. Okay? So I required that it have David Bowie but not have Iggy Pop. And it turned out that it had Iggy Pop. So the whole thing was false. So you can roll your own. We can have a community of people. I'm always finding weird things, like, for instance, some people on the Datapunk group gave me some information. I think Natalie gave me one on something to do with kids. And sometimes things are just, they're so simple that they just don't really even warrant being an algorithm. You know, I mean, what if you found an article that said, well, RS1234 GG is associated with increased risk of earache? You know, you can make an algorithm out of it. It would be a one SNP, one outcome algorithm. So, I mean, it's not going to be terribly interesting, but it would make a terrific cluster because it's just so easy. And it's a simple, you know, sort of quick and dirty way of doing it. And then if it turns out that it's really valuable, you know, when you save the cluster, because you can do this up here, you give it a name and a short description, and then you tell the program, hey, I want it in my toolbox. I want this cluster associated with this particular client, and I want to share it with the community. So that, for instance, when I show up the next day, I go, wow, there's a cluster there that shows that there's this association that somebody came up with. Cool. And I got just the person I want to run that on. Right? So that's the algorithms part. And prescriptives, as I said before, we have psychic. So here we got VGEF. I'm doing stimulate bottleneck. Well, let's say we use another gene like mTOR. Oh, that should be interesting. Everybody's favorite gene. And we want to inhibit drain. So in other words, I want to stimulate drain. That'll really mess them up. I'm going to stimulate the guys upstream. I want to do something bizarre. I'm going to stimulate bottleneck. For instance, you might want to do this if you're in a situation where you're treating a cancer patient. I want to stimulate what's upstream, and then I want to choke it off at the stuff that's downstream. Bear with me and pray that this works. Okay, there we go. So what we're doing now is, these are all the things, and it turns out that if you want to stimulate downstream of, actually I take that back, this should be upstream here, but yeah, that's just one of those crazy things. This was when I was working on this morning. You'll find after a while that things get crazy, and You run them and then you go, oh God, I misspelled something. I got to go back and spell it right. Anyway, the program itself is quite reliable. It's just there's a word change here that needs to be made. So it turns out here, if I wanted to basically stimulate mTOR upstream and then block it downstream, well, astragalus would be pretty good. Turmeric and scutellaria would be pretty good. Epicatechin 3-gallate would be good. And this also tells you the genes that are there that are problematic. They could be also looked at further. And then the other prescriptive one is Phantasmatron. Okay, like I said before, it's going to be two things. You can go into here and say, hey, I want to look at elements of the diet that I'm interested in playing around with. But what it will do when it comes up is it's going to first tell you what it thinks you should do, as every good piece of software should tell you something that you don't know. And so when it first comes up, it's going to go to Mona Lisa, run all the SNPs that are associated with nutrient things, and then it comes back and says, hey, guess what? I think you should increase the total amount of folic acid in the diet, increase the vitamin D, decrease the sodium, phosphorus, increase the butyric acid, increase the betaine, get rid of the malvin phenolics, and get rid of the gluten. And by the way, increase glucosinolates. So what would happen, and this part doesn't work yet, I was just working on this morning, you're going to push a button, it's going to go into, some of you guys use Swami, so you know that the Swami nutrient database is really phenomenal. It's really one of the best food nutrient databases in existence because it has everything from traditional Chinese values on foods to overgrowth values to anything, in addition to the USDA values. So then you would hit the button, it would go in and go, hey, since you're looking to do these things, have the client try to emphasize these foods a little bit more. And if you're looking to restrict these things, make sure the client takes these things, is aware of these things. So in this case, you can see sometimes, in this case, what I have here is a blank box, because sometimes certain things you could, for instance, certain things might be warranted to increase or decrease depending upon the patient. So if instead of decreasing sodium, I wanted to increase it, I would click that. If I want to decrease, I click that. And if I want to totally just turn this off, I click that. But there are some things that there's no rational basis to do one or the other. And so this comes in blank here. So for instance, in this case, doing nothing is the same as that. So niacin only has an option to try to find things that are rich in niacin. And then you can set it for things like vegan and stuff like that. You can use the blood type. If you use the blood type values, it'll calculate ABO blood type and secretor status and things like that and factor that into the calculations. So you got, basic category. If you're a Swami user, you're going to see some similarities to the matrix in Swami. And it does basically use the same data tables and stuff. So then the only final thing is the reporter. So, but that's again in process, as I said. So at this point, you might say to yourself, okay, now I've done all this and that. What am I going to do? How am I going to present this to the patient? How am I going to chart it? Well, when this is up and going, you would say, okay, I'm going to make a client report. I want it verbose. I want to limit it to high magnitude SNPs. I want to include the SNP table. I want to include the LUMEN algorithms. And I want to include the GWAS results. And by the way, tell me the natural products. Then you hit the button and out comes the report and you print it. So, and that part's pretty straightforward. Can I pull data in from Swami Pro? Ryan Partovi was really asking me about that. And the reality is yes, it could easily. The reality is that that'll eventually be something I'll bolt on because it really is easy to do. The only problem is that Swami resides on one server and Opus resides on another, but there's even a way to get around that. So the answer to that is yes. If you have, let's say, a Swami Pro person, you would put in their client ID and it would put that stuff in as well. And you can use that as a departure as well. Do the recommends from the come out in the written? Yeah, I guess so. Do the recommendations from Phantasmatron come out in the? Yes. So yeah, the idea is this stuff is the easiest part to write. You know what's really the hard part to write is what I'm writing right now, which is the account management part. Oh, hi, Peter Diadamo. Welcome back. Oh, by the way, you've got 8 things left on your license and this and that. And the problem is it's so boring. It's so boring. And it's just all this file input output. Very, very uninteresting stuff. And if you put me in with the genomics and tell me that, oh, I'm going to make something really flashy here with a beautiful graph, I can be at the computer for 10, 12 hours. But I do this account stuff and this file input output. I do about a half hour, and then I want to go upstairs and go to sleep. So I'm grinding through that. That'll be done probably in another week. Then I have to do the report thing. That'll take a couple of days. Then I have to do the Phantasmatron thing. That'll take about a day or two. So that's the situation with regard to that. The last thing I want to do is I'm going to lift up the skirt and show you a little bit of the editor behind the scenes stuff. Okay, so because I'm an editor, because I'm just special, I get this editor thing here. And it says, oh, snip, let's go list this. So we'll list this. Let's go look for MTHFR. All right, where's the biggie? Oh, there he is. So now we load this thing into the editor. This is what an editor sees that's based upon everything that he does or she does with a SNP. This is all the information that's presented about that SNP that they use to make their determinations about the value of that SNP, about the use of that SNP, keywords, all sorts of things. So it's really just an incredibly, you'll notice here, this part's interesting because the first thing that Opus does is it tries to get the strands right, okay? So allele of interest is consistent with strand orientation. What's the DB SNP orientation? How do I convert it? And then it goes around and converts it. So any given moment, like I said before, an editor or a curator is sitting in the most densely populated information about that SNP in probably one of the few places that you can make these kind of changes and make these kind of decisions. Now, the interesting thing is that you remember this? No, this. Okay? When this is done, an editor will have this linked to the SNP. So, for instance, when he's working or she's working on the SNP, they can then program what the particular nutrients are to be looked at in detail for that SNP. And then that can be used elastically in the algorithm. So we can say the algorithm, okay, provide nutrient therapeutics for this algorithm, and it come back and say, okay, well, SNP 1, 2, 3, 4 is got an association with generally wanting to watch allergens. It's got an association with toll-like receptor 4, so we have to watch out for overgrowth issues, and so on and so forth. So, see, like I said before, the boring part is making the stalk. The fun part is making the cauliflower outside, because that's where you can make all the interconnections that continue to sort of enrich things. And I think I said it on generative medicine. Enriching data is just really the equivalent of enriching uranium. You just keep doing it until it gets better, and 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 it gets better. So, really what I see here with this program is a classic demonstration of what generative medicine can do and what it's capable of doing. And to take a philosophical aspect, and you talk about heuristics, and you talk about complexity, and you talk about, and it's all talk. And then when you see it work, when you see it take something complex and make it real world significant, make it simple, decomplexify it, make it intuitive, you see that generative medicine is about the closest you're going to get to being able to put your hands on the vis medicatrix in some way that you're going to be able to you're going to exercise both sort of growth channeling and developmental and remove obstacles. And, you still have other things, obviously. The thing that I said before to one of my students was that these types of technologies are like word processors. They make you a better writer, but they're not going to make you Mark Twain. Matter of fact, Mark Twain didn't need a word processor, right? He probably would have been a better Mark Twain if he had one. But the truth of the matter is that the technology is here to propel where you want to go. It isn't there to take you there. It isn't there for you to say, okay, now I just I abdicate everything, so just tell me what to do next. Okay, that's why the teaching part's so important. And, in essence, really, to be able to have that discovery process makes you able to see your way to asking the next set of questions. And, the best answers always lead to the next questions. And this will, evolve for, well, I don't know, it'll just keep going and going. But as it is, there is, as far as I can tell, a very small chance that these functions are being duplicated anywhere. And these are just the results of having had a couple of months to think about things that I would like to have. So they're not any great, insight into things other than just these are cool things that I think I would love to be able to have at my disposal. But I can tell you this, I mean, who would want to know if the patient in front of you has a higher placebo effect than someone else? I think that's a pretty useful piece of information. There's an algorithm for that. And if you look at it that way and you realize that there's nothing threatening about a word processor, it's not going to make you any less of a person. It's not going to make you it's not going to make you a worse writer. It can be abused, obviously, but a word processor is a tool. And with this, it's the same thing. It's a tool, but it's a growing tool. And it is, I think, a wonderful opportunity for us to be able to see if we can tap into what it was that I think was at the crux of what being a naturopathically inclined person was from the beginning, which was, treat the person, predict and prevent and personalize, right? The 4 Ps, and participate. The participation part is to get people to take this and to use this information intelligently and to use it over the long term. 4 Ps are all embodied in this piece of software. And the nice thing about it is that, again, it's not designed to be exclusionary. It's not designed to, make it hard. I mean, we want to make sure the right people use it, but we want to make sure that when they use it, by the time it all gets put together, the person at the other end is going to feel that the whole thing was well worth it. But as I said to my students as well, once this thing is in the clinic, everything before it was in the clinic will be essentially the equivalent of the Bronze Age. That ultimately everything we did before was neat, but it's never going to be the same. It's never going to be the same again. Because at any given moment, we will have information about that patient, the likes of which we never had before. So there was a question about the mapping, power mapping. So let's find a methylation. How's that? Let's go look at 1-carbon metabolism. So power analysis basically tries to understand where the person is coming in terms of the capacity of that gene to produce its particular protein byproduct. So we know that most genes code for proteins, and most of the proteins that are coded for genes are enzymes. So we can use information on the catalytic ability of the enzyme and approximations of the catalytic ability. Again, it's sort of like the psychic program where you go up and you go down, and you try to calculate really how much substrate is going to be produced at the top of this gene, how functional is the gene, and how much substrate can be estimated on the other side of the gene that can be picked up as the upstream part of the next gene and what happens there. So the idea being that you're trying to get an idea for the degree of substrate that's running around that's being catalyzed by these genes. This is still not exactly what I would consider to be, at this point, foolproof. It's only a rough approximation, but it's still a darn good rough approximation versus the fact that given at this particular moment in time, we have zero approximation. So I hope that helps, Marcus. It's really more a question, like I said before, it's like, how much can you expect this particular gene to process whatever amount of substrate is arriving upstream, and how much it will, because of that and because of the degree of function that it has, because of the degree of mutations that are occurring inside of it, how much can be anticipated is going to come out the other side that will be available to the next thing down the chain. Right? So, that's about the best approximation I can give you. These maps, I mean, this is methylation. Let's see. I was working on one the other day. This is neat. This is circadian oscillator. So, for instance, these are, things where you're looking at sleep deprivation, the disrupted sleep cycles, things like that. So, is it done? No. But it's kind of interesting that really it's still got a much more potential, but it's amazing just how functional it is given the amount of time that we've been working on it, and the fact that the amount of time that has to be, you have to balance it between, okay, do I sit around and draw a map and fill it with data, or do I make a program that draws a map? It's kind of, you're still juggling between those two things. So I don't know. Is there any other questions here? Let me see. Is the dark blue more functional? Yes. And when you see a purple, it means that the complex is being augmented by mutations that convey extra functionality. Most of my patients come with their data interpreted environment. Okay, let me see if I understand. Most of my patients come with their data interpreted via current available channels. So that would mean that they've already gone to NutraHacker or MTHFR.net. Wouldn't matter to me, because what you would do is you would just download the raw 23andMe data in here. So, for instance, what would happen with regards to this is you would go up to here where it says Manage, and there would be a link that says load new client, and then you would have the raw file on your hard drive. Click on that, the program would load it, it would parse it, it would create the patient account. And as far as, for instance, I don't know if by the question you mean would it be willing to take any of the other data from the other reporting services? With all due respect, I don't know if I would want it. Most of the things that they've done, we've looked at where where there were very good things, we frankly tried to incorporate them in this program. There's like, a lot of different criteria, and I think with many of the programs, they're really good at what they do. Like, for instance, the MTHFR.net uses the Sterling's app for what it does, which is a simple reporting type thing in tabular format. It's wonderful. And I have to say, and I don't give this accolade out lightly, it's one of the few things that doesn't make mistakes. Okay? When I look at most of the other things, they're just full of mistakes. So with Sterling's app, you have a wonderful tabular type thing. And if that's essentially where you want to go, that's the degree of that you want to work with it, then it really does the job fine. It doesn't do more than it promises, and it does that well. With this, I mean, I want to know, hey, what do I do for this thing? What are the changes? How does this fit with that? Does this particular thing work with this other thing? And if this thing and that thing are present in this way, what does that mean? So I think a lot of that is more a question of, sticking with the raw data part of the whole thing. And I mean, I haven't set it up to take any of the other data forms like Ancestry.com or Illumina. They're all the same. I mean, in 10 minutes, I could come up with a filter for Illumina and a filter for Ancestry. They're all what are called tab delineated text files, just big old text files with data. So but the reality is that ultimately 23andMe is like the 800-pound gorilla at this point. I mean, and think about okay, so you spent $99 for a 23andMe analysis. Now you got all these SNPs. Now you have your little Opus 23 professional account. You paid your money. You pay $50 if you're INGM, $65 if you're not. You run and this is what you're looking at, okay, for $140. And again, we want to have the COEs make money. I mean, we have expenses and stuff. So we thought that's a pretty reasonable price, for an hour and a half of our residence time, for an hour and a half of our physician time analytics, and to be able to have the time to do a good job. Now, go out and Google what other people charge, and some people charge like 10 times this amount, 5 times this amount, 6 times this amount. And again, I think that that's what I feel most like is that. Okay, I got more questions here. 23andMe uses proprietary data format. Can we import you as a? Well, there's a question. It says 23andMe uses proprietary data format. It isn't proprietary in any big sense of the word. It's just a big old flat text file with tab delineated. So and that's not a big thing. VCF, I don't even know what that is, but I could find out. Can we import genetic data in other formats? Yeah, I wouldn't see there would be a big issue. Of course, that question was asked by my resident geek. But yeah, I mean, if we can take that to another conversation, Kent, and we can talk about that in any way that might work. Certainly figure it out. Can SUPERMOGADON run overlapping maths, sort of like a fuzzy duck function? No. The reason being that the SUPERMOGADON maps they're hard drawn, and the fuzzy duck maps are dynamically generated. And the reason that the not the SUPERMOGADON, the regular mapper function, the one you're looking at now, the reason that I went with the hard drawn maps is that if you use a program to dynamically generate networks, sometimes they just become very difficult to read. And what we wanted was to actually use software to hand draw the maps so that they were the most intelligible that they could be. Now, in order to have the ability to mix and match maps, I would have to be able to dynamically draw the map, take the parts of one map, take the parts of another map, put them together. And whereas that can be done, you can't control how that lays out. And most of the time, it just lays out terrible, and it's very difficult to read. Will this interpret blood type and secretor status instead of having to run blood work? Absolutely. Yeah. I mean, we could get that information very easily. Yeah, it turns out that there's only like 2 SNPs you need to get secretor status. One of them calculates secretor status for almost everybody in the world. And then I think a second one kind of is used to calculate secretor status in people who are mostly Japanese or Korean. That's easy enough. Uh-oh, we lost sound. I hope you got the sound back. Do you intend on adding epigenetic data to this program when it becomes more widely available? I can add anything to this program. So, in other words, when we have reliable, data, data is just stuff. It's just text words, data, numbers. If it can be put into I'll put it to you like this. I mean, data is anything that you can probably put into Excel. If it's got rows and columns, it's data. And if it's got rows and columns, I can muck around with it. That's about the story. So the answer to that question with regard to epigenetic data, or any data, in fact, is if it's got rows and columns, yeah, we can do anything we want with it. And that column data and the row data is what gives it all the variability. So, I tried to find what were some, hopefully, things having to do with epigenetic relationships. It's still in the infant stage in many respects. Yeah, I have sound. Okay, sounds okay to me in UK. All right. When can we have a webinar on the other programs within the INGA, Fuzzy Duck, Qualibet? I don't know. I mean, we'll schedule another one of those at some other time. I'll show you how to use that stuff. Right now I'm working on this, though, so, I'm kind of like thinking to more or less just keep working on this. I'll be working on this until at least the first of the year, and that'll be the first build. And then I'm going to rest my eyes for a while and think about what I want to do and when I want to add it. And then some point maybe in the spring, I'll start work on a second build that'll have the next version of things that we put in. And I would love, anybody who has ideas and feedback to just message me on the Datapunk group and give me your ideas. And I've gotten lots of ideas. I mean, Tom Greenfield and Jackie Greenfield have been very, very helpful in terms of coming up with concepts and ideas and things. And people at Val Prescarou, and I mean, so many people have come up with just wonderful feedback. And the great thing about it is, like I said before, if you can make a condition out of it, and somehow or another you can figure out how to make a column in a row, I can probably do it for you. Anyway, all right. So we got that. Please repeat the 4 Ps you mentioned. This is from, who's that? Leroy Hood, Institute of Systems Biology. Predict, prevent, personalize, and participate. Wonderful presentation. Oh, thank you. Can you add SNPs that are not in 23andMe? Yeah, we have SNPs that are not in 23andMe. The only problem is since how would you know what the outcome was unless you had some other way of being able to get that data? In other words, I suppose if you ran, let's say, the Illumina, one of the things I find very interesting is that has a lot of possibilities is the Illumina metabolome stuff that they're doing. Again, it's hard to do much with microbiome, because I mean, you could have a different section of the program that looked at, some sort of manifestation of the microbiome in terms of amplification of bacterial elements that might be some part of an analytic framework. The difficulty with that is that it's still not much data, but I think if there's within the next 5 years, I suspect this program there'll be a component that will be, all right, we ran their poop and, we got all these glycosyl transferases and all these other things, and we want to run that in and cross-reference it with their capacity for CD14 and toll-like receptor 2 and toll-like receptor 4 because we want to activate the NOD1 and NOD2 signaling for a person who might have autoimmune sensitization. There's all sorts of ways you can do things. I mean, that's what I said before. If you get the stalk right, the cauliflower follows. You can do anything you want. We can add anything we want. Like I said, this would be difficult for me to imagine that I even be here 3 years ago, But it's beautiful because guess what? Computers are digital and genes are digital. Okay, you got C, you got T, you got G, and you got A. And then you got a number, RS1234. It doesn't get more simple than that. And the question is how you mix and match and how you ask the questions. That really pretty much determines what the outcome is. So anything that's going to stay in that format is a perfect environment. Digital genes, digital computers, and then out comes an analytics. And then at that particular point, you, the physician, are on your own. Away you go. All right, I'm going to knock it off. I think I ran a little late here. Thank you so much. Everybody seems happy enough. So pay close attention to the Datapunk page, and I'll keep updating. And then as we get closer to that point where we feel comfortable, we'll take it from there. And as I said before, though, if you ask me to summarize this, and I'm only talking in light of my own anticipation in my own practice, my own teaching shift, it's never going to look the same way once we start doing this. Nothing's ever going to look the same anymore. The patient's not going to look the same. We're going to be informed on a level about things that's going to be so much more different. And, I think that's, as I said before, it's almost like a Stone Age, Bronze Age kind of thing, or a Bronze Age, Iron Age. It's like there's no looking back. Okay, well, thank you very much for being so patient and going through this with me like that. And there's so many people from all over the world. I know some of the people in Australia are up like around 1 o'clock or 1:30. I think it's great. And we got people in England, and we got people in Turkey, and people in California, and people in the Northwest, and people in New York. So wonderful community, and it's been a lot of fun. I can't tell you. I mean, I get up in the morning, and it's like I get up and I go, I just figured out how to do this. I just figured out how to do that, and then I go to work. After I do this for a couple of hours, I go to the COE and work. So it's a great life. But it's been my pleasure, and have what little left of the weekend. I hope you enjoy it, and we'll see you real soon.